All right, here's some more of these Lagrange problems, and this is number 5. And we want to find the square root of 0.8. And there's, you know, I can think of 3 ways to do this, and I think I did it a couple ways. And you could say, well, why don't you just let f of x be the square root of x about 1, and you could do that. Okay, it'd come out the same, believe it or not. I've looked it over, and it'd come out the same way, so down the bottom, your error bound will be actually exactly the same. So, and that might be interesting to see how this is parallel. So what I did was I thought of 0.8 as 1 plus negative 0.2, and that would give me 0.8. And I just thought of f of x as the square root of x plus 1. And I'm going to be looking for f of negative 0.2, and that's going to give me the square root of 0.8. So it might seem like a crazy way to do it, rather than just use the square root of x and 0.8 about 1. Okay, you can't take the square root of x about 0. It has to be about 1. But you can take the square root of x plus 1 about 0, and that's fine. So you got a couple ways to do this. So probably you tried it the other way. And if I have time, I'll do that other one and that other solution and put it up. Like I said, I should have told you which ones to use. Okay, but let's just go on with this. Okay, so the derivatives look a little more complicated, but actually the expansion is easier. So, like I said, 6 and 1/2 a dozen the other. So I use this about piece of 3 about a sub 0, a equals 0, that's the center. And then I just took my derivatives, and I started with the square root of x plus 1. And we didn't have any SIGNs here to bother, so we just took our derivatives just like if it was x, so it would work out exactly the same. And those are your derivatives. And then I put this in the general form, and there's my expansion, and I simplified it. That was my expansion. Now the tricky part is that since I want the square root of 0.8, my x is going to have to be negative 0.2 because it's negative 0.2 plus 1. That was the function. So I put negative 0.2 in here, and this is what I would get. Now, if you expanded it around the square root of x, at a equals 1, you would put 0.8 in, and you get the same thing. So I guess this might be a little bit of a bizarre way to go at it, but it works. Okay. And in class, I could do it the other way if we need to see that. That's no problem. Pretty fast, as a matter of fact. Okay, so let's find so this was our approximation. So this was the A part, this was the polynomial expansion, and this was the approximation. So let's find the error bound. So I have to take the fifth derivative. I'm sorry, the fourth derivative, because this is just the third order. So we'll take the fourth derivative, and we want to bound that. And it's going to give us our Lagrange error bound, M. If I can find an M that's going to work for this. So I looked at this derivative, and if I took the next derivative up here, if you look up here, that's going to be positive 15 over 16, x plus 1 to 7/2. And this is going to be on the interval now. What I'm using for x now is not 0.8, but I'm using the negative 0.2 for the x, so I've got this interval like this. So this is my x and this is my a, and this is going to give me my approximation. Like I said, it seems a little bizarre. And you can see as x increases, this decreases, so I'm going to evaluate this at negative 0.2. So if I put this in, and like I said, the expansion is a little bit easier, but then this part's a little bit harder, but you end up with the same thing. You get it at 0.8, so it works out the same. Because negative 0.2 plus 0.1 is 0.8, and this is where, since it's decreasing, this will be the maximum value of the upper bound for the derivative, so it works out to be end up being the same. So if you were doing it, if you expanded it as the square root of x about a equals 1, but you use 0.8, you'd end up with the same M. And then But you would have x minus 1, so you'd end up with the same 0.2 also, so your work will look the same. Okay, so it's curious the way that works out. So you have some leeway here. So anyway, so we looked on this, and this was easy to see. So I put the negative 0.2 as my value of x for the bound for my derivative. So m equals this, and this will always be smaller than this. There's my bound here. Okay, and then I just have to worry about this x and to the fourth power, the absolute value, and 4. And on this interval, the highest value, the absolute value of any element of this interval will be 0.2. All right? 0, no, 0.2. That's that's the biggest. The farthest away from 0 will work out. So this is going to be m, which is this, 15 over 16, 0.8, because that was negative 0.2 plus 1 because it's from my derivative, all right, times 0.2, because that's the maximum x can be on this interval, the absolute value of x, all right? Not negative 0.2, but 0.2 because it's the absolute value, to the fourth over 4, and this is what we get. All right? Let me get this up a little higher, sorry about that. So I'm really probably inclined to do this again using the square root of x, because I think it would be a little bit, it would end up with the same thing. So anyway, so I just chose to do it like this. You could choose to do it either way. And I even used 1 minus x. I did another way, so you could do it that way also. Okay? But anyway, this will give you, something to look at, so you can take a look at this, and hopefully that makes sense. And I guess it's not bad to do the same problem 3 different ways. It just takes a little bit of time. So sorry about that. Okay? And let's take a look at number 6. And number 6, we just want to find the expansion. First, this is a little different. So I just want to find the expansion. First of all, we want to find p sub 3 of x at a equals 1. So we gave you a center here for this function. So we just take our derivatives. I'll find my problem over here. There we go. Okay. So determine the Taylor polynomial for the function at x equals 1, which is the center, a equals 1. Okay, so it gives us some more direction, and I probably should be more specific the next time I give you those problems, or the next time I give problems like that. Okay, so I have f prime of x, this is my f double prime, this is my third derivative. So we evaluate those. That's pretty much straightforward. This is kind of that little factorial pattern we've seen in these functions when we have these fractions, and those are my derivatives. And again, I'm about x equals 1, so we just put this in the Taylor expansion to general form, and then we simplify it. And again, you can always pause this if I'm going too fast. Make sure everything looks right. And this is what we have. So this is our simplified third order polynomial expansion. That's what we wanted. And then we wanted to find the error on an interval. Now this is different. We didn't give you a particular value. We just said on an interval. Show that the polynomial approximates f of x to within 2/1000th on the interval. So now we're given the interval, so we don't have to calculate that. Okay, so it's not like we're trying to find at 1.5 just on this interval. It'd be the same idea if I asked you to find p of 1.5. So I took my fourth derivative, which is going to be 24, 1 plus x to the fifth. That follows that pattern on this, and then on this interval this is decreasing, so because as x gets bigger the derivative gets smaller, so this is decreasing, so my m will be the maximum value, so I can bound that, so that's going to be at 1. So if I put 1 in here, I have 24 over 1 plus 1 to the fifth, which is 24 over 2 to the fifth. So that's my m. So this is my error. It's going to be less than this is my m. And then I want to maximize this. So this will be easy to maximize. X minus 1 is going to be maximized at 1.5 minus 1. Definitely not 1 because that would be 0. So 1.5, that's going to be maximized that there. At 1.5, so 1.5 minus 1 is 0.5, so this is what we have. And then we can simplify this. 24 and 4 factorial are the same, aren't they? That worked out really nice because this is 4 factorial. So those canceled out, so we just had 0.5 to the 4th over 2 to the 5th, and we can have, if we work that on our calculator, I got 0.00195, and that's definitely less than 0.002. Because if I carried that out, that would be 0.00200, and that's 0.00195, so this is less than that. Another way to do it is you could work it out arithmetically. You could think of this as 1/2 to the 4th over 2 to the 5th, which is 1/2 to the 4th times 1 over 2 to the 5th, which is 1 over 16 times 1 over 32, which is 1 over 512. And this is smaller than 1 over 500. Because this denominator is smaller than that, that makes this fraction bigger than that. So this is bigger, and this is the same thing as 2 over 1,000, which is that, 2,000. So that's another way to look at it. Okay, so I hope you can follow those. Hope that helps.